General relativity, step by step. We now have all the ingredients, all the mathematical machinery in order to define the Einstein field equations. And this is really the highlight of Einsteinian relativity. It really is the most concise, brilliant condensation of all the mathematical and physical reasoning that we've been doing over the last few weeks into one very, very small equation. So I'm going to spend some considerable time talking about it and discussing it and deriving its various properties and so forth. It's going to take a long time. I haven't quite decided how to cut this up yet, but there might be 7 or 8, maybe a dozen screencasts. Okay, well, let's go back to Newtonian dynamics. Newton was pretty sharp, and let's just write down the equation for, I'll just write it down and then I'll talk about it, equals 4 pi, because a sphere has got area 4 pi r squared, g rho. There's our Newtonian dynamics. This thing here is the differential operator. Is it the Laplacian, that one? I can never remember. Laplacian, I think. It's di 2 by di x squared plus di 2 by di y squared plus di 2 by di z squared. It's that thing there. This thing is the gravitational potential energy. Gravitational potential energy. I guess if you had to measure it, you'd measure it in joules per kilogram. 4 pi is just a numerical constant. I'll come back to that numerical constant because it bothers me very much. Well, not this one, but the field equations equivalent bothers me, and I'll talk about that. This is the Newtonian gravitational constant, 6.671 times 10 to the minus 11 in SI units. So this is force equals g m1 m2 over d squared, Newton's inverse law of gravitation, and it's this thing here we're talking about. And this is the density. So one thing's for sure, when we try to generalize the Newtonian mechanics, or generalize Newton's, it's not quite Newton's law here, but the equation that governs the Newtonian potential. When we try and generalize that to the relativistic case really ought to reduce down to this, in the limit of slow velocities and low pressures and low speeds. So it's got to reduce down to the Newtonian case. It's also, the generalization also has to have another property. It needs to be covariant. We need to be having correctly formed tensor equations, because whatever we replace this thing with here has got to work in any coordinate system. And we'll see that this way of thinking, this requirement that our thinking and our equations have to work in any coordinate system, is a very fruitful line of logic indeed. So what are we expecting? Well, I can't prove this, but what I really want is a tensor. I'm just going to call it x alpha beta equals some constant k times t alpha beta. And I'll talk about these things in order. This thing here is the stress energy tensor. Stress energy tensor. Why? Well, because Newton's equation here, or the Newtonian potential law, has got a density, and we need to replace the density with something that makes sense relativistically. This is a constant of proportionality, which will have a g in it. It'll be a g. But at the moment, we don't quite know how it's going to work. There might be factors of pi floating around. This factor of pi might not work properly. There might be factors of 2. There might be factors of... any numerical factor might go in there. So I'm just going to write it as a k. This thing, we don't know. It must be a second order tensor. And we think it's got something to do with the curvature of space. And so it's going to be some second order tensor with two upstairs indices. Why two upstairs? Because this one's got two upstairs indices. And so this will give us a system of equations. But just looking at it for the moment, we know that T alpha beta equals T beta alpha because we know that the stress energy tensor is symmetric. So the right hand side is symmetric. So that tells us that X, whatever X is, will be symmetric as well. Well, it's a start, I suppose. Yeah. Okay, so it's symmetric. What else do we know about the stress energy tensor? T alpha beta, we know that this is the case. In the literature, you quite often see it used. You quite often see this notation: alpha beta equals 0. But I'm going to try and stick with the semicolon notation, purely because I can use the comma goes to semicolon rule, which is my favourite principle of all in the whole of physics. Well, one of my there are many of my favourite principles, but the comma goes to semicolon rule is certainly up there on, yeah, certainly up there. Okay, so we know that the right-hand side of this equation here, I'll just write it out again because I'm running out of space here, X alpha beta, we don't know what X is, equals some constant times T alpha beta. This means we must have, taking the covariant derivative of both sides gives us X alpha beta semicolon beta equals K T alpha beta semicolon beta equals K T alpha beta semi beta, which equals 0 because we proved that a few screencasts ago. So summing up, we know that whatever X is, it must have a covariant derivative of 0, and that will constrain us in our search for X. Okay, I'm going to stop there, and I'm going to talk about, next time I'm going to talk about some candidates for what X might be. Stop.